Homework 20, hypothesis test for mu, sigma known, video 4. Testing mu, the critical value approach, video 2. This is actually an example of how hypothesis testing is used in certain industries. The scale needs to be calibrated. A weight known to weigh exactly 1,000 grams is weighed 50 times. The mean of those weighings is 1,000.6 grams. The scale must be recalibrated if we reject mu equals 1,000 at a 10% significance level. Should the scale be recalibrated? Use sigma equals 2. All right, this kind of screams hypothesis test because we're talking about rejecting a claim. We have a significance level, and we have a sample comparing or challenging what we claim about a population. All right, let's go through the 5 steps. Step number 1 is to state the hypotheses. I haven't said this lately, but when you state the hypotheses, H0 and H1 are abbreviations for the phrases null hypothesis and alternative hypothesis. They are not variables. You do not put them equal to things. You put colons after them and then make the claim about the population that you're testing. In this case, we're explicitly told that mu equals 1,000 is one of our hypotheses, and being equals must be the null hypothesis. Now, let's think about what the alternative should be. We want this scale to be accurate. We don't want it to be out of whack. So what would a good alternative hypothesis be? Our choices are greater than, less than, or not equal to 1,000. The best alternative hypothesis should say not equal to, because if the scale is weighing things too heavy, it needs to be recalibrated, and at the same time, if it's weighing things too light, it needs to be recalibrated. In other words, whether it's overweighing or underweighing is bad. So we need to test that the mean is not 1,000 when we weigh this 1,000 gram weight 50 times. All right, let's set up our bell curve with which tail or tails? Because the alternative has not equal to, that means this is a two-tail test. So evidence showing that it needs to be recalibrated could be on either side of the bell curve. What is the area of those tails? Well, collectively their area is 10%, but there are 2 tails, and therefore the area must be cut in half. Each tail is 5%. So the area of each tail is 0.05. But for z-chart purposes, we will append 2 zeros. We've already discussed locating 0.0500. Its z-values on the left where z equals negative 1.65, and on the right where z equals positive 1.65. So those are our critical values, separating the critical regions, the tails, from the middle. If our sample converts to a z that is either less than negative 1.65 or greater than positive 1.65, we will reject the null hypothesis. Speaking of the sample, we need to calculate the test statistic. Recall that statistic compared to parameter is a sample value. So basically we're using our sample value to test our claim. Our test statistic starts with calculating sigma sub x bar, which is the sigma, in this case 2, divided by the square root of the sample size. So what's the sample size? Answer, the number of times that we weighed this weight, 50 times. Ooh, I think I might be able to do this one mentally. Give me 1 second, just trying something. I'm going to say this is about 0.28. That's the best guess I can get. Now I'm going to say 0.2828. I didn't do the math in my head. Can't even find my calculator. I used some trickery. Ask me outside of class or outside of this video, and I'll explain what trickery I did to correctly predict that this is 0.2828 to 4 decimal places. Wait, we're not done with the test statistic. That's simply the denominator of the formula. Our test statistic is z equals a difference over the sigma sub x bar. So the 0.2828 will go in the denominator. Our difference comes from what we observed from the sample, which was 1000.6, minus what we're claiming about the population in the null hypothesis. We're claiming that the population mean is 1000. This is going to be a really small value because the numerator is just 0.6 divided by 0.2828. Did I say small value? I meant to say large value. Well, it's all relative, but z equals 2.1216 if you round it to 4 decimal places. Dang, I should have stopped while I was ahead. Got that, totally botched this up in my head. Okay, so we found the value of our test statistic, and now it's a battle of the test statistic versus the critical values. In other words, go to the picture and ask yourself, where does this z value that came from our sample land relative to our critical values? Well, it's positive, so it's to the right of the middle, and it's greater than 1.65, which means this test statistic lands past the critical value into the critical region. When your test statistic crosses the boundary into the critical region, you reject. Reject the null hypothesis. So what does that mean contextually? Should the scale be calibrated? Well, we recalibrate if we reject mu equals 1000, and we just did. Therefore, we must recalibrate. Whatever business we run, we cannot tolerate 1 kilogram being measured by an error of 0.6 grams. I'd hate to speculate what kind of business this is that is so worried about measuring 1 kilogram and being off by about half of a gram, but I'm sure you can speculate. All right, so what can we take from this example? Number one, the critical value approach runs the same course. State the hypotheses, sketch the critical regions, and determine the critical values. Convert what your sample gave you into a z so that you can compare it, and if it lands in the critical region, reject the null hypothesis. Also, in a two-tailed test, don't forget that the area gets split in half. All right. What if this were 5% instead of 10%? Don't worry, we're not going to redo the whole problem. If this were 5%, it would get cut in half in 2.5%. And in a previous video, we saw that the critical values when the tail was 2.5% was 1.96. So even if it were 5%, this would still cross over. If it were 1%, I don't think it would. So your decision does depend upon your significance level. Basically, the larger the significance level, the bigger the area of the tails, and the less tolerance you have for deviating from the middle. So greater significance level when it's more important that your measurements be accurate, a lesser significance level when you can tolerate your measurements being less accurate. In the next video, we're going to look at the alternative, or another approach called the p-value approach. In the homework, you have some problems that ask you to do the p-value approach. The good news is you really don't have to do much different work than what we've seen here. You just have to do something slightly different and make a different comparison. In fact, for the p-value approach, you even don't technically have to draw a picture.